Welcome to Discrete Math Module 1 Lesson 2. This module covers set operations. Module 1 Lesson 2 outline covers the following topics. You have set operations, cardinality of union of sets, set identities or laws that govern your sets, computer representations of sets. Let's begin with operations on your set, starting with union of two sets. The union of two sets A and B is a set which comprises of elements that are either found in set A or in set B or both, mathematically denoted by this given symbol. In your Venn diagram, we illustrate the union of A and B like this, whereby the shaded region in your given Venn diagram comprises of all the elements included within the union of your set A and B. To be more discrete, let's evaluate this given example, whereby we have a universal set comprising of numbers 1 to 9. And then we group numbers 1 to 5 and call it set A. Likewise, we group values 3 to 8 and call that set B. Then the union of your set A and set B would comprise of values now 1 to 8. The next operation involved is called the intersection of two sets. The intersection of two sets A and B consists of all elements contained in both set A and set B, mathematically denoted like this. On the Venn diagram, this shaded region involves the elements that are found within the intersection of A and B. To be more discrete regarding intersection, let us take, for example, our universal set U, which contains values 1 to 9, and then grouping values 1 to 5 as set A and grouping values 3 to 8 as set B. The intersection of A and B now would comprise of elements 3, 4, and 5, which are common to both set A and set B. There are also instances whereby sets do not have any elements in common. These are referred to as mutually exclusive sets or disjoints. When they are represented in your Venn diagram, they look like this. Note that set A and set B do not overlap since they do not have any elements common between them. Likewise, these sets A and B are subsets of your universal set. The next operation is referred to as complement of your set. The complement of set A comprises of elements that are not contained in set A. However, these elements are included in your universal set. When depicted on your Venn diagram, it actually looks like this. This shaded region outside your given set A pertains to the elements that are included on your complement of set A. To be more discrete regarding this operation, let's evaluate again our given universal set, which contains values 1 to 9, and then set A containing values 1 to 5, with set B containing values 3 to 8. If we then try to establish the complement of set A, that would mean elements 6, 7, 8, and 9. And the complement of your set B would mean values 1, 2, and 9. Note that when evaluating the complement of your given set, it is also equivalent to your universal set minus that given set, which is why some textbooks prefer to call this operation as absolute difference. The next operation is known as set difference. This involves in the difference of two sets within the universal set, which is often denoted as relative difference. If we then apply set difference on set A and set B, bearing the symbol A minus B, it would then contain the following elements, which are elements found in set A, but all the elements common with set B are removed. Therefore, on your Venn diagram, this particular shaded region represents A minus B. On our given discrete example, whereby set U contains values 1 to 9, and set A containing values 1 to 5, with set B containing values 3 to 8, A minus B would then comprise of only elements 1 and 2. But if we do it the other way around, B minus A now would only contain values 6, 7, and 8. The next operation is referred to as the symmetric difference. The symmetric difference of A and B this time involves the relative difference of A minus B and B minus A, defined to be the union of A minus B with B minus A. On your Venn diagram, it is illustrated to be this shaded region found in your Venn diagram. The symmetric difference is often given by the symbol of plus enclosed in your given circle. To be more discrete regarding this operation, let's take for example our universal set U with values 1 to 9, our set A containing values 1 to 5, and set B containing values 3 to 8. The symmetric difference of A and B now would contain the difference of A minus B, which involves the elements 1 and 2, and the difference of B minus A, which involves in the values 6, 7, and 8. Therefore, the union of this corresponding differences would mean your symmetric difference, containing the values 1, 2, 6, 7, and 8. Some particular sets contains elements that are grouped together, which are referred to as ordered n-tuples. It's basically an ordered collection that has A1 as its first element, A2 as its second element, and so on and so forth. Two n-tuples are equal if and only if their corresponding elements are equal. The two tuples are called ordered pairs. The ordered pairs A, B and C, D are equal if and only if your value for A is equal for C and your value for B is simply equal for your D. These particular sets are often seen on what you call Cartesian product. This operation involves in multiplying elements found within your set. So when you say Cartesian product, it's often denoted as A times B. It is basically the set of ordered pairs A, B, whereby A is an element of your set A and B is an element of your set B. Therefore, when we create the Cartesian product A times B, we're actually forming pairs of elements that are ordered in the manner of A, B. Let's take this discrete example. Let's say we're given set A to contain A, B, and set B containing values 1, 2, and 3. Therefore, if we multiply A times B, we'd end up with the following product pairs: A, 1, A, 2, A, 3, B, 1, B, 2, and B, 3. Note that these particular pairs are ordered based from the ordering seen on your multiplication, since A happens to be the first set and B happens to be the second set, therefore all product pairs will contain their first element coming from set A paired together with elements that are seen on your set B. The Cartesian product, therefore, involves in a set of ordered n tuples, which may contain more than 2, which belongs to be elements of set A paired with other elements that are multiplied to your given set. This is one such example. Let's say we wanted to evaluate the product of A times B times C, where A contains 0, 1, B contains a set of 1, 2, and C contains a set of 0, 1, and 2. Therefore, we'd end up with the following ordered pairs. Note that there are now 3 elements on our given groups, whereby the first element of each group comes from set A, paired with the next element coming from set B, paired with, again, the element coming from set C, making up, therefore, an equivalent of 12 possible groups of 3's. The next operation is known as the cardinality of the union of sets, which basically counts off the number of elements included within your union of set, just like the cardinality of your set. Now, in the cardinality of set, we often apply what you call the principle of inclusion-exclusion in order to determine the exact number of elements that are found within each region of your corresponding union of sets. So the technique is applied on particular sets that may contain 2 or 3 given sets, mathematically stated as this for 2 sets and this for 3 sets. Note that the parallel bars between these particular operations represents the number of exact elements that are within those given particular sets or groups. The next part of the slide covers what you call the set identities. These set identities are the different governing laws on your respective sets. Numbers 1 and 2 represents what you call the identity law. Numbers 3 and 4, the domination law. Numbers 5 and 6, the idempotent law. Numbers 7 and 8, your commutative law. Number 9 is called the double complementation law. Number 10 and 11 is referred to as your distributive law. Number 12, your absorption law. Numbers 13 and 14, your symmetric difference. And numbers 15 and 16 represents what you call the De Morgan's law. The following set operations are likewise performed by your computer. So the question there now would be, how would my computer represent those corresponding sets? So there are several ways to represent sets on your computer. The simplest one is what you call a bit representation. A bit is simply a binary value, either 1 or 0, which eventually represents as your digit. Hence, a binary digit, or bit for short, represents either a value of 1 for true or a value of 0 for false. Note that you may represent any particular value on your set using 1 or 0 by simply string up together all of these given bits. Let us then try to apply computer representation now on the following sets. We have our universal set U containing values 1 to 9, and its subsets set A containing values 1 to 5 and set B containing values 3 to 8. The length of bit string that represents every given set on this particular example would comprise of 9 bits, since your universal set U contains 9 elements. Therefore, when we represent a value, we then replace that with 1 or 0. 1 if that element is present on your given set, and 0 if that element is not present on your given set. Therefore, your set A will be represented as this bit string, whereby, seen on your universal set U, the first 5 characters on your set are present on your set A, valuing 1 to 5, while the rest of the elements 6 to 9 are not present on your set A, therefore it's represented with a value of 0. Hence, your set B is then represented with this bit string. Likewise, you can represent any set operation using bit string. Let's say we wanted to evaluate the complement of A, and we already know that the complement of A comprises of the elements 6, 7, 8, and 9. Thus, the bit string representation of this would then be this equivalent bit string. If we evaluate now complement of B, which comprises of this time values 1, 2, and 9, you would end up now with this following bit string. And finally, for A union B, whereby the set comprised of values 1 to 8, this now would be your respective bit string. The computer representation now for the intersection of the following sets, A and B, would then be equivalent to this bit string, since we know that the elements on your intersection set would only be 3, 4, and 5. The set difference A minus B would now have this corresponding bit string, because we know that the elements in your bit string would only be 1 and 2. And for B minus A, it would now be this bit string, because we know that the elements inside your set are simply 6, 7, and 8. Let's try to evaluate a few more examples regarding sets. Let's say our universal set S comprised of the following elements of your periodic table. You have copper, nitrogen, oxygen, potassium, sodium, uranium, and zinc, with set A comprising of the elements copper, sodium, zinc, set B comprising of the elements nitrogen, potassium, sodium, and set C containing oxygen. Let's try to list down the elements now found in the following events. You have complement of A. The complement of A now would contain nitrogen, oxygen, potassium, and uranium. A union C would now comprise of copper, sodium, zinc, and oxygen. A intersection B would now comprise of only sodium. When evaluating a more complicated set operations like this, then we evaluate the operations inside the braces first. However, if there are several operations inside the braces, then we simply follow the hierarchy involving your set operations, which is complement first, followed by intersection, followed by union, followed by your other operations. So in this case, we then evaluate first the complement of B, which comprises of copper, oxygen, uranium, and zinc. And then afterwards, we then evaluate A intersection of complement of B, which gives us copper and zinc, Then evaluating complement of C would give us copper, nitrogen, potassium, sodium, uranium, and zinc. And finally, the union of these events would give us copper, nitrogen, potassium, uranium, sodium, and zinc. For letter E now, we evaluate first the complement of B, which gives us again copper, oxygen, uranium, and zinc, with complement of C again giving us copper, nitrogen, potassium, sodium, uranium, and zinc. Thus the intersection would give us copper, uranium, and zinc. In evaluating then letter F, we start off with complement of A containing nitrogen, oxygen, potassium, and uranium, and complement of A union B having nitrogen, oxygen, potassium, uranium, and sodium, and complement of A intersection with C being oxygen. Thus, the complement of both events would simply be oxygen. Let's evaluate examples this time involving cardinality of your union of sets. Given on this example, a mathematics professor has been keeping track of the excuses given off by his students for missing his class. He then discovers that 65 of them said their dog had a flu, 70 of them said their car would not start, 30 of them said they needed to bake cookies, while 12 said both their dog had a flu and they needed to bake cookies. 8 said both their car would not start and that they needed to bake cookies. 5 said both their dog had a flu and their car would not start, while one person actually used all 3 excuses. And it was found that there were 95 students who did not use any of these excuses, but actually gave a different excuse. From this problem, if we are then asked the following, how many of students were in the professor's record? How many students had only one excuse? How many students said their car did not start? How many students said only that they had to bake cookies? And how many students had exactly 2 excuses? To answer then that problem, we will apply the principle of inclusion-exclusion with your Venn diagram. So on our Venn diagram, we would have 3 groups labeled A, B, and C, referring to the group of students who gave off A, the excuse that their dog had a flu, B, the students who gave off the excuse that their car would not start, C, the students who gave the excuse that they suddenly needed to bake cookies. And out of those groups of students, there were mentioned that 95 did not use any of these excuses. Therefore, they do not belong to any of this group. Hence, they are placed here on this part of the Venn diagram. One person used all 3 excuses, therefore he is the intersection of all events. 5 used both A and B, therefore that leaves us only with 4 on that region. 8 used both B and C, therefore that intersection region already contains 1, that leaves us with 7 here on this region. 12 used both A and C, and again that region already contained 1, therefore only 11 is placed on this region. And out of the total students who mentioned that they suddenly had to bake cookies, they said 30 of them belong to set C, that leaves us only with 11 on this region. 70 said they belong to set B, that leaves us with 58 now on this region. And 65 said they belong to set A, that only leaves us with 48 on this region. In answering then the following questions, how many students are actually in the professor's record? We will then sum up all of these values inside our given universal set. So we end up with the following solution. Summing up all these values gives us a total of 236, which is technically equivalent to the formula for the principle of inclusion-exclusion plus the complement, which also gives us that same number. In evaluating letter B now, wherein we're asked to determine the number of students who had exactly one excuse, they are these students who belong to this region, the 49, this region, the 48, and this region, the 11. And if we sum them up, you would end up with a total of 118. The cardinality notation for this particular region of event would now comprise of the union of all events minus the intersections of all of these events, and then we compensate for 2 of the intersection of all events. For letter C now, if we try to determine the number of students who did not say their car would not start, that would mean, of course, the 49, the 11, and the 11, plus the 95, which in turn should give us a total of 166. The cardinality notation for this particular given event is now referred to as your complement of B. In evaluating then letter D, whereby we are asked to determine the total number of students who only mentioned that they needed to bake cookies, that amounts to 11, which basically are these students that are within this region, having a particular cardinality notation equal to this value, which is the union of all events minus A union B. In evaluating then letter E, whereby we are asked to determine the number of students who exactly used 2 excuses, that would only mean the following values. You have the 4 here, the 7, and the 11, amounting to a total of 22, with a given particular cardinality notation equal to this particular expression.